Hello everyone, we are from Group 3 and this video is prepared for KM46103 Advanced Welding Technology. My name is Iza Aidila binti Azman and this project was carried out together with my group member Ahmad Nur Firdaus bin Saidin, Norshifa Nadira binti M. Nasril and Jessie Derenje Mojiun. In this assignment, our group focused on welding metallurgy and microstructure analysis. The welding parameter selected is the number of welding passes, where double or multi-pass welding was performed at a constant current of 80 ampere. Through this video, we will demonstrate the preparation of the welding sample, hardness testing, microstructure observation, and explain how welding parameter influence the strength of different welding zone. This video shows the preparation of the welding sample. At this stage, the welding sample preparation is carried out in the workshop. First, the base metal is cut to the required size. After cutting, the edge of the sample are angled to prepare the joint geometry for welding.
My name is Jess Darren and today I'll be explaining on our welding processes or the workshop preparation. But first, what is welding? Welding is a process of joining metals by melting and fusing them together. But to achieve a strong and safe weld, a proper preparation, the correct current setting, and correct welding technique are very important. But for our project, what is the parameters? So we set up the parameters as we use a current of 80 amperes and we are using a welding technique called the multi-pass welding. From here you can see there are two videos, which is here, the welding phase, and also here, after the welding, what did we do? But first, before the welding starts, several preparation steps must be done. So first of all, the metal surfaces must be cleaned because dirt, rust, oil, and paint are removed to avoid weld defects such as porosity. Porosity is like a gas bubble trapped inside the metal, as you can see from microscopic image. So second, the joint edges are prepared grinding for thicker metal. A V groove, which is 45-degree, is made to allow deeper penetration of the weld. As you can see from previous slides, we make a 45-degree angle so that to make a deeper penetration for therefore a better connection of between two metals. And then the workpiece are aligned and clamped properly to prevent movement during welding. So what did we do? After the angle of 45-degree of both metals, we align them properly so that it doesn't move, and we make it like stick together on the welding table on the workshop. So the welding machine are also checked to ensure proper cable connection, electrode condition, and correct polarity. So for this one, what intrigues me the most is that the electrode condition. So from that, we called it the filler material, like a stick. So we checked whether the shielding gas is sufficient or not to also prevent the welding defects. And lastly, the safety equipment, such as the welding helmet, as you can see, the visor, the welding visor, the gloves, and also the apron must be worn to protect the welder. Because as you know, a higher melting point, it might burn your skin alive too. So you might asking yourself, what is multipass? Multipass welding means the welding of the joint using one more layer than the other passes. This technique is used when the metal is thick enough and the joint needs a high strength. one single weld pass is not enough to fill in the joint. So the first pass is called the root pass, which is the very bottom of it from the 45-degree angle. This pass ensures a deep penetration into the joint. And then the second pass and third are called the filler passes, what we did. So we only did three passes, the root and the second and the third. These three passes will fill the joint groove and increase the joint strength. The final pass is also called the cap pass. This pass gives smooth surface finish and full joint coverage. Between each passes, the weld slack is cleaned using a chipping hammer and wire brush to avoid defects, as you can see from this video here. So, in conclusion, during welding, there's the safety reminder, which is wearing a full PPE, the personal protective equipment, keep flammable materials away, ensure a good ventilation, and also avoid direct eye contact and skin exposure to the arc light. So the good welding quality depends on the proper surface and the joint preparation. Also using the correct settings, which we set up at around 80 ampere of current, and using multi-pass welding technique for a thick materials or to have a high joint strength. These steps ensure a strong, safe, and reliable welded joints. Thank you.
After the welding process, the specimen was prepared at Pusat Rejang for metallographic analysis. A section was taken from the welded plate near the joint areas so that the both weld region and the surrounding heat affected zone were included. The specimen was then trimmed into a 20 by 20 mm piece, which is suitable for surface preparation and microscopic. And the surface was polished using a mechanical polishing machine until a smooth and scratch-free finish was obtained. After preparing the sample, we conduct a Rockwell hardness test on the base material. The measured hardness is 28.9 HRC, which indicate medium carbon steel. The carbon content affect the formation of microstructure during welding and influence the strength and toughness of the weld and heat affected zone. After preparing and etching the sample, the microstructure was observed under an optical microscope. The image shows different regions of the weld joint, which include the weld zone, mushy zone, heat affected zone, unaffected zone, and fusion line. The weld zone located at the center of the weld experienced complete melting and solidification. The grains here are coarse and irregular due to the solidification process. The mushy zone is a transition area between the weld zone and the husk. Partial melting occur in this region, resulting in a mixture of solid and liquid phase. The heat affected zone is next to the weld zone and experience high temperature without melting. Grain growths occur in this region due to thermal exposure, which may reduce toughness. The unaffected zone is far from the weld area and retain the original base metal microstructure with fine and uniform grain. Finally, the fusion line separates the weld metal from the husk and marks the boundary of complete melting during welding. This observation helps us understand how heat input and welding parameters affect the microstructure of each zone, which in turn influence the strength and toughness of the welded joint. Thank you. That's all from me.
So I will explain briefly the solidification process and the phase transformation of steel using the iron carbon phase diagram. When steel is in molten state, it exists as liquid iron with carbon dissolved in it. As the metal cools, the liquid begins to solidify and the first forms a phase called the austenite. Austenite is a high temperature phase that can dissolve a large amount of carbon. As cooling continues, the temperature drops below about 723 degrees Celsius. Austenite becomes unstable and transforms into two new phases, which is the ferrite and cementite. These two new phases arrange themselves in layers to form a structure called pearlite. Ferrite is a soft and ductile, while cementite, also known as the FeC, as you can see from the slide, is a very hard and brittle. Perlite is a combination of both, so it provides a balance between strength and also malleable toughness. So, in simple terms, the transformation is liquid metal turned into austenite, and then austenite transformed into ferrite and perlite. The cooling rate is very important because slow cooling produces core structures with lower toughness, while faster cooling produces finer structures with better mechanical properties. So, in conclusion, the iron carbon phase diagram helps us to understand how steel changes structure during cooling and how these changes affects its final properties. So right now I will explain more about mechanical properties concisely and briefly. So there are two, which is the coarse grain and also excessive heat. But I will explain more about how the grain size and heat affect the mechanical properties of metals, especially the strength and toughness. In metallurgy, the internal structure of metal, called the grain structure, plays a very important role in determining how strong and how tough a material is. But what is a grain? What is grain? What are grains? Grains are metals made out of many, many small crystals, as you can see from the microstructure. So this size of grain depends on the cooling rate, the heat input, and also the welding or heat treatment process. If the metal cools down slowly or receive excessive heat, the grains become coarse and more larger. If the metal cools faster, the grains become much more fine or smaller. You can see and you can deduce how we did in the microstructure analysis of our slide for ours. So coarse grains and strength. Coarse grain metals have fewer grain boundaries, less resistant to dislocation movement, more brittle behavior under impact. But about excessive input, let's make this briefly. But about excessive heat input during welding or heat treatment, what does it do? What does it cause? It causes the grain growth, the loss of fine microstructure, and also reduced mechanical performance, because when the grains become much more larger, too large, the materials loses its toughness, meaning it has and become more likely to crack or fracture suddenly. Brittleness. So why and how did we determine this problem? I would say it's a problem in welding. Maybe you're using too high of a current, maybe you're too slow on your travel speed, or maybe you're doing many passes without it cooling properly. Unevenly distribution of heat. This can cause excessive heat input, resulting in a weak HAZ, the heat affected zone, reduced impact resistance, and also a higher risk of cracking. How to control this problem? To avoid coarse grains and low toughness, we should use a correct current input and voltage. We also control the heat input and use a proper cooling time between passes and use the correct welding technique. So, in my opinion, for this stuff, these mechanical properties, for welding especially, it is heavily dependent on your skill on welding. So there's many theory, but at the same time, you need the technical skills and practice to ensure to create a good welding. Like we said just now earlier, call a correct welding technique. Maybe you didn't let the welding rest enough. Maybe also you are using a low current, or maybe you are welding in one spot a very long time. So, in conclusion, the grain size strongly affects mechanical properties. Coarse grains reduce toughness and strength reliability. Excessive heat causes grain growth. And finally, controlling heat input is essential to maintain a strong and tough metal. That is all.
In conclusion, the number of welding passes and the carbon content of the base material significantly affect the microstructure and strength of the welded joint. The weld zone, HSZ, and machi zone show different grain structure that influence toughness and hardness. So proper control of welding parameters and understanding of metallurgical effects are important to achieve a strong and reliable weld.